In this video, we are going to introduce structural induction. So we will talk about the method and do our first example. So structural induction is a form of induction that is helpful for proving things about recursively defined sets and structures. Okay, so here is how it works. If I'm trying to prove some statement is true for all the objects in some structure that I'm going to call S, using structural induction, there are two steps. There's a base step and there's an inductive step, much like with our other inductions that we've seen. Okay, in the base step, we show that the statement is true for all of the elements that are defined in the basis step of the structure's recursive definition. So what does that mean? We've seen examples of recursively defined sets before. In fact, let's just briefly take a look at this example, and then I'll finish talking about how induction works. So here's a set that's defined recursively. And I started off with the basis step. In the basis step, we describe what are the elements that we know are in the set kind of initially. So this one says 6 is an element of the set. Okay, and in the recursive step of this set's definition, it says that if x and y are in S, the set, then x plus y is going to be in the set. So the recursive step gives us a rule for constructing new elements from old ones that we already have. Okay, so in structural induction, in the base step of it, what we do is we show that whatever it is that we're trying to prove is true for these initial elements. So for my example, I'm going to try to show a certain thing is true about this element 6. And in this example, what are we trying to prove? We are going to try to prove that 6 divides any element of our set. So in this base step, I would try to show, well, that 6 divides this. 6 divides 6, which we can see is clearly true, but we'll write it down in the proof. Okay, that's the base step. In the inductive step, what we do is we assume that the statement that we're trying to prove is true for all the elements that are used to construct new ones in the recursive step of the structure's definition. And then based on that assumption, prove that implies the statement is true for the new element. So what does that mean? So in this inductive step, what I would be doing, for example, in this example, is I would think about my assumptions / what I'm given, and then what it is that I want to show. So this inductive step of structural induction says, well, the statement I'm trying to prove, which is that 6 divides x, let's assume that that's true for these old elements, the ones that I use to build new ones. So let me label these. These are like the old elements. The old elements. And then x plus y is the new element that I get. The new element. So in the inductive step, we assume that whatever it is that we're trying to prove holds for these old elements. Okay. So for my example, I would be assuming that 6 divides x, and I would be assuming that 6 divides y. Okay. And then what I'd want to show is that this statement that I'm trying to prove holds for the new element, x plus y. So I would want to show that 6 divides x plus y. Okay, so I'm going to put this in a little thought bubble. Okay, and you might already see or kind of have an idea that, like, yeah, I expect that to be true. But, we will put that all together in this proof. Okay, so let's tackle it. Let's prove this thing using structural induction. So we begin with the base step. So in the base step, I look at the initial elements that we have in the set's recursive definition, which says 6 is in the set. So in my base step, I'm going to be looking at the element x equals 6 and asking myself, well, is this statement that I'm trying to prove true for this initial element? Well, okay, so in other words, does 6 divide 6? So yeah, because 6 is equal to 6 times 1, where 1 is an integer. So the fact that, 6 is a multiple of 6, it's an integer multiple of 6, means, so I can say, so as a result, that's the definition of what it means for 6 to divide 6. Okay, so the base step holds. The base step holds. Cool. So we are done with that. All right, so we are on to the inductive step. So in the inductive step, remember, again, we assume that the statement that I'm trying to prove, that 6 divides these elements, we assume that that's true for the old elements that are used to build new ones in this recursive rule. So the old elements are, in this case, x and y. So I'm going to assume that x and y are in S. We let these elements be these old elements in the set. I start off by saying that, such that, and then I'm going to assume that this property holds for these two elements, that 6 divides x and 6 divides y. That is my inductive hypothesis. Okay, and now I break down what that means. Okay, so it follows, what does it mean to divide? It follows that there exists a k and a j that are integers such that x equals 6 times k and y equals 6 times j. Okay, and what I'm hoping to show is that 6 is going to divide x plus y. So let's add the two equations together. So then, adding them together, x plus y will be equal to 6k plus 6j. And I can factor out a 6 to get that 6 times k plus j. Okay, and that's kind of what I wanted. I wanted x plus y to be equal to 6 times an integer. Let's just relabel this thing in the parentheses so it's really clear that it's an integer. Okay, maybe I'll label that as m. Let m be k plus j. So we get that x plus y equals 6m, comma m is an integer. But that's precisely what we wanted. You know, this implies that 6 does divide x plus y. That's the definition of what it means to divide x plus y. So we've reached what it is that we want to show. So now we're ready to state the conclusion, which is by structural induction, the result that we wanted to prove is true. 6 does divide x for all x in the set. Okay, then I draw my square, fill it in. We are done with the proof. Our first structural induction proof, done it in the books. Okay, so in the next video, we will tackle another example, and we will kind of up the difficulty to show, you know, what the power of structural induction really is when we have more complicated recursive sets that we're working with.